So this talk explores the needs that arise when you're running a cluster scheduler at scale. But the first question you should really ask yourself is, why should I use a cluster scheduler in the first place? And I think there's a lot of reasons to use a cluster scheduler, but if you start categorizing them, you'll start seeing three clear themes. And that is, firstly, the benefits for developers, operators, and the business. And for developers, the main thing that you gain from adopting a cluster scheduler is this common workflow for all applications. And that's largely because the scheduler isolates developers from the underlying infrastructure it's running on. So if a job developer is working in AWS or Azure or even a private data center, the workflow they experience is the same across all of them. And on the other side, they can deploy code much faster and safer with a cluster scheduler with the primitives it provides. And that kind of leads into the benefits that operators get. Because this shift away from machine image per application, the operator's responsibility largely becomes maintaining a shared infrastructure that all developers can benefit from. And because there's no longer this heterogeneous mix of applications, each doing their things their own way, it becomes easier for operators to configure, monitor, and productionize the shared infrastructure. And because of these, since operators gain higher leverage, since all the work they do impacts all developers using the shared cluster, operators gain huge leverage. And developers don't get outside of their core competency as much because they spend less time deploying code. And the resources that you do pay for, they get higher resource utilization. So this all adds up for the business to save money and increase efficiency. But I'm not that concerned about the business use case in this talk. We'll mainly focus on operators and developers. So should we all use cluster schedulers then? The unequivocal answer is no. But I think that statement, there's a lot to break down, and I think it's interesting to dig in and see why we shouldn't all pick cluster schedulers. And I'd assert it breaks down to roughly this. The benefit of a cluster scheduler is a function of your scale and the complexity of the cluster scheduler you pick to adopt. And I'd like to break down each of these terms. Scale might seem very obvious. The most obvious dimension is your cluster size. Are you running 10 nodes or are you running 1,000 nodes? The benefit you get at those scales are very different. But I think the non-obvious dimensions are how many developers do you have? How many applications are you deploying? And at what rate are you deploying applications? Because since deploying applications traditionally does take time, the faster you want to do it and the more people you want doing it, the more things that can go wrong and the more cost there is to the organization. So these are important dimensions as well to consider when adopting a cluster scheduler. Next, you have cluster scheduler complexity. A lot goes into this, so I really am summarizing this a lot, but I think it breaks down into these few things. There's the initial setup time. How long does it take you to build a production-ready deployment of that scheduler that you've chosen? And if you look at that a little closer, I think the more important thing is how many components does it take to deploy the cluster scheduler? Because for every component a cluster scheduler takes to be operational, that's another responsibility for operators to maintain, to upgrade, to configure, to make sure it's reliable. So there's a high cost to this complexity. And then you need to look at the reliability of a cluster scheduler. As you grow and you rely more and more on it, if that base infrastructure that everything is running on isn't reliable, your organization is going to run into a lot of pain. And lastly, ease of upgrades. And I think this comes back into the architectural complexity of a scheduler a lot. When you're deploying this as your base infrastructure, you want to be on the latest versions with the newest security patches, reliability fixes. So you don't want to pick a cluster scheduler that's so overwhelmingly complex that you don't feel comfortable to upgrade it because you might introduce downtime. So I think that is why these two things are kind of the dominant variables in the benefit of a cluster scheduler. And I think it's an interesting exercise to actually kind of plot what the benefit of a cluster scheduler would look like if you just fix the complexity and plot it against the scale. And if you had a zero-cost cluster scheduler, it would look something like this. The benefit of the scheduler would scale linearly with your organization's size. When you're very small, developers benefit from the lifecycle tools it gives you. It's easier to deploy. Your operators configure one thing. Everyone's happy, right? But this is unrealistic. There's no software that scales like this. And then if you fix complexity on the other end of the spectrum, I think you end up something with a curve like this. There's probably a lot of ways to draw this, and I'll explain why I think it looks like this. When you have a highly complex scheduler that you're thinking about deploying, when you're in small scale, it's not worth the initial setup cost. You're better off using simpler solutions. But eventually, your organization keeps on growing, and the benefits outweigh the cost, and you decide to deploy the cluster scheduler. But that's kind of the peak benefit of the scheduler. As you keep on growing and you put more and more into the scheduler, if you don't feel comfortable operating the scheduler, if you have reliability problems, you now have put all your eggs in one basket that you can't monitor or upgrade or trust. So really, that's why I think this slopes back down. So with this in mind, I want to explore kind of the scale spectrum of clusters and what we did when building Nomad and what kind of drives the features and the implementation. Because our goal is to kind of try to be this zero-cost scheduler. This is obviously the ideal that everyone writing software should shoot for, to be as easy to operate and use. So we keep this in mind. So I want to start exploring the spectrum at n equals 1. This seems like a very odd place to explore a cluster scheduler, but when we first set out to build Nomad, we actually considered this case very carefully. And that's why we introduced Nomad Agent Dev Mode. What Dev Mode does is it runs a real Nomad client and server on your local machine. And it stores everything in memory. So you can bring it up and shut it down cleanly. But what it lets you do is, when you're first learning the tool, it lets you get comfortable with it because you can interact with the client, hit every API, learn the commands. And once you are comfortable, it's actually really nice to use to develop the job specs you use in production and QA, because you can take the same job files you use, change maybe the resources to scale it down so it can run on your MacBook or whatever, and then you can just run it. And as you want to play with changes to your job file, you can experiment locally. So we want to make it the Nomad as a cluster scheduler usable and simple even at n equals 1. But there's really not much more to say at a cluster size of 1. So next is at a scale of roughly 10. At this point, you're more or less getting your feet wet with a cluster scheduler. You might have one or two applications in it. And I think the goals that a scheduler should aspire to at this scale is to get operators to the point where they're writing realistic cluster configurations and they can productionize the scheduler. And for developers, it's to ease the transition away from this single application per node model into operating within a cluster scheduler. So what are the features we do to help operators at this scale? The first is we use a very human-readable configuration. Anyone who's used any of our tools is probably familiar with HCL, the HashiCorp configuration language. And so I want to show you what it would look like to bootstrap a highly available 3-server, 10-node Nomad cluster. This would be the server configuration. Datadir says, please write your data to this directory. Server enabled enables the server. And Bootstrap expect says, please run with a quorum size of 3. And the client config would look like this. Write your data to that directory and enable the client. And you would run 10 instances of this. So how the heck does this give you a 10-node cluster? That's because we do sane defaulting. So when you run this job spec, Nomad will read that, set all the things you set and specified, but then we'll default as much as we can. So we'll default the region, the data center. We'll look at the host name and set a appropriate node name for you. We'll fingerprint the networking to figure out what addresses to bind to and what addresses to advertise to the rest of the cluster. But we still didn't show the servers connecting to each other. So how do they discover each other? Well, we do auto bootstrapping via console. So if you run this config, another thing we'll add is this console block. By default, Nomad will look for a console agent running alongside of it. And what we'll do is when Nomad comes up in server and client, it'll register itself as a service with console. And once it's registered itself, it will actually go read the catalog and find other Nomad servers and other Nomad clients. So when a server comes up, it'll find console, register itself, and find, hey, I'm running in region foo. What other servers are in region foo? And then automatically bootstrap a highly available cluster for you. So with just those like 4 lines of code, if you're running console alongside of it, which is highly recommended, you get a near production grade cluster. And this might seem hyperbolous, but it really isn't. If you're running Docker, what you really should add to that config is your Docker auth, where to read the configs, maybe an auth helper. But that config would actually work perfectly well. And we do other things to make the life really easy for operators. There's no external data store. So when you bring up those servers and they bootstrap themselves, they'll automatically use Surf to connect and use Raft as a consensus protocol. So all servers have the same state, and you're highly available. And Nomad servers and clients run the same binary, can read the same configs. So you could even refactor configs and share them between each other. So we make it really, really easy for operators. So what do we do for developers? We do 3 things, I think, to help ease the transition. And those are an even deeper console integration. We try to help simplify the lifecycle of applications and help introspection when things go wrong. So if you run a Nomad job, the topology is something like you have a job, jobs have task groups, and then tasks are embedded in task groups. And those are what are running on your cluster. And task groups let you run multiple tasks co-located together. So within a task, you can add a service block. And what this service block does is it'll register a service with console. And if you look at the bottom of the screen, you'll see we have a resource block. This task is asking for one dynamic port named the database port. And Nomad will just pick an ephemeral port on one of the available IPs for you. So you may not know what port you're on until it's been placed on a node. So with this service block, what Nomad will do is once it's placed, it'll register the service with console so other applications can discover you within the cluster. And the embedded checks, which you can add, then run health checks against your task so that you know whether the task is healthy or not. So what we do is we automatically register, as I said, when the tasks start. But another cool thing you can do with this service block is you can deregister before you kill the allocation when maybe you're doing a rolling upgrade. And this lets you, with legacy applications, to start draining connections. So you might deregister, and then since no one can discover it, you can't make any more requests to a service. That application can handle those services till there's nothing left. And then Nomad can kill it, so you don't get any drop services. And we also support registering both the host and container IPs with console in the case that you're using overlay networks to make that easy for you as well. Next, we want to simplify the lifecycle. And what I mean by this is when you have a single application per node model, it's really easy to wrap your binary with some shell scripts, run chef, do whatever you need to get it to run. But you have a little more constrained environment when you're using a scheduler. So the first thing we do is we have this artifact block, which lets you download any assets that you need for your task to run. So you can download binaries or config files or whatever else you need, and Nomad will automatically decompress it if it's a tar or a zip. And it can also download stuff from S3 in any HTTP or HTTPS data source. And if you add checksums, it'll even do checksum validation for you to make sure you're running what you think you're running. So applications need their binaries, and they also need config files. So we have this template stanza. And what this allows you to do is embed configurations inside your job spec or download them externally and run them there. But it's very powerful because you can read environment variables that Nomad sets for your application, like that Nomad port. You couldn't have known it beforehand because it's dynamically allocated based on availability. So you can read it from environment variables, set it in your config. But it also allows you to read data from console as well. So maybe you want to read what's a service key that you should make when talking to another microservice. You can read it from console. And if that value ever changes, Nomad will detect that from console, rewrite the config, and you can signal the application to reread that, or Nomad can restart it for you. And this same template also allows you to do dynamic environment variables in the case that you're running 12-factor applications and you want your config via environment variables or flags. So if you set env equals true, Nomad will read this as an env file and populate the environment for your application. Another cool console integration we have, and this is a new feature in Nomad 07, is when you specify a check, you can tell Nomad to restart the application based on the health of this check. So in this stanza, we say, if this check fails 3 times in a row, I want Nomad to restart the task for me. Maybe it's got stuck or it's hit a deadlock, and I just need to restart the application to get running again. And you can do that. And the grace lets you say, hey, this application may be unhealthy as it boots up, so don't consider any failures for the first 90 seconds. So that's really cool, too. So those are some of the features that we have for Lifecycle. There's more, but I want to keep going. Next is introspection. Not everything goes well when you're in Cluster Scheduler. Maybe you put the wrong config, or you don't have auth, and you want to see what's happening. So it's very easy to introspect with Nomad. You can do Nomad alloc status, your alloc ID, and we'll show you the recent events, whether the allocation has restarted and whatnot. So at the bottom, you can see, oh, this application exited with code 1, which is an application error. So maybe let's take a look at the logs to see what happened. And you can do that. You can do Nomad log, and you can tail and follow logs to monitor what your application is doing while you're trying to debug. It also provides Nomad FS, which gives you a way to look into the file system of a task. So maybe it was the case that the rendered config had a typo, and you need to see what was wrong in the config. You can navigate the file system remotely. So those are some of the things we do as you're getting your feet wet with the cluster scheduler. But at scale of roughly 100 nodes, you have more applications in the scheduler now. You're not just playing with it or doing a POC. So at this scale, safety is really becoming critical. And for the operator, their job and responsibility now shifts into securing the cluster internally and externally. So what are some of the features we provide to allow operators to do this? The first is TLS encryption. You don't want your data flowing unencrypted, so Nomad makes it very easy. You add this simple TLS block to your servers and clients, and you'll get encryption on both HTTP and RPC. So all data that might be sensitive will be encrypted. And we also do role-based server name resolution. So this is a cool feature that means that a client can't masquerade as a server. They have different certs that give them different privileges. So that's cool. Next is Vault integration. This could be its own talk, and as a matter of fact, it is. So if you're interested in learning more, I suggest you watch that talk. But at a high level, what the Vault Nomad integration allows you to do is you can set up a Vault role that essentially delegates certain operations to the Nomad servers. So when a user submits a job asking for certain Vault policies, the Nomad servers can derive a token that gives that application only access to the policies it needs. And then the client that runs those applications will retrieve that token and start renewing it for you. So in the end, what an application gets is a very high level. They say what policies they need, and then they get both secure introduction, which for anyone who has actually used Vault is the hardest thing to do. So you get secure introduction, and you also get automatic token renewal. And to make it even more secure, we don't ever store the token in the servers. The servers are actually never exposed to the token. There's lots of hoops you jump through to make that happen. And even on the clients, we only store the token in memory. So we make the token available in an in-memory file system to the application. And we also make the Vault token available in the template block that I showed you earlier. So in this example, we have a task that asks for a Vault policy that gives them access to the front-end policy. And that policy might give them access to certain secrets, etc. And then in the template block, you could just render a config that says, I want you to go out to Vault, read the API key secret, and write it to this config file. And so with that simple block of code, the application gets a Vault token. It's securely introduced. It's renewed automatically for it. Nomad handles reading and renewing the secrets from Vault. And all they do is read a file. It's really cool. And on the back end, to configure this as an operator, you more or less create the role in Vault. You tell Nomad about the role. You give it a token that allows it to create other tokens from that role. And you tell it where Vault is and the certs you need to talk to it. That's it. Next are two new features in Nomad 07, namespaces and ACLs. So namespaces allow you to isolate teams and users from one another and all their jobs and all the associated objects with them. And ACLs allow you to not only do enforcement on all of Nomad's HTTP endpoints, but it really gives you fine-grained access control to who has access to each namespace and what they can do in it. So here's a Nomad job. With the new namespace feature, you can annotate it and say, I want this job to run in the payments API namespace. This is our, let's say, payment API server, and it's sensitive, and we don't want every developer in the company to have access to it. So what you can do is you can create the payments API. The first line there creates the payment API server. You can Nomad run that job. And then if you do Nomad job status, you'll see no jobs running. That's because by default, you're in the default namespace that everyone has access to. But if you switch to the payments API, you can see that job is there, isolated from everyone else. But anyone can just write payments API, right? You didn't do much. ACLs is the thing that allows you to enforce who can do what with each namespace. So our ACL system is default deny. So for anyone, once you enable ACLs, for someone to have access, they need a policy that gives them access to a namespace. So we can write this policy, the payments policy, that says on namespace payment API, whoever has access to this policy can have write access. And then what we can do is the first line here just says for all the following CLIs commands to run in the payments API namespace. Let's say we have a bad actor who wants to disrupt our startup's cash flow. So they might want to stop the API job. Well, they'd get a permission denied because they don't have an ACL token that allows them to do anything with that namespace. So let's say you are a good actor and you actually want to stop the job because it shouldn't be running. What you can do is you can do token create with that policy, and it'll print out the accessor and secret ID. The accessor ID is not sensitive. It allows you to see the policies associated with the token. But the secret ID is. So if you set the Nomad secret ID and then run Nomad stop, Nomad realizes that secret ID gives you permission to that namespace with the right policy, and allows you to stop and interact with the job. So with those three features, the cluster operator can create an externally and internally secure application, and developers can easily access Vault, so they don't really have an excuse. So what do we do to make developers confident at this scale to be deploying their applications? This is an exciting one. Not everyone is comfortable to work in CLIs all day. So with Nomad 07, we're introducing a web UI. The web UI is a great way to look at your job, introspect what it's doing, any failures, and it's pretty cool. I want to just show a few slides of it. So this is the job overview view. You can see what's running. Your batch job, which computes profiles, has finished. If you dig in, you can see, OK, I have 3 running. They're healthy. You can even dive further in and see the allocation events, what ports they're on, et cetera. And this will fill out over time. Next is rolling deployments. So Nomad has rolling deployments. So when you have a job file that maybe you're doing an upgrade of the Docker image to run from 0.1 to 0.2, Nomad will detect when that change is destructive. So when it's a destructive change, it'll look for what we call the update stanza. The update stanza allows job operators to tell Nomad how they want their job to be updated. So in this case, the operator is telling Nomad, hey, I want you to update my job one at a time. And every time you put a replacement of the job, I want you to make sure it's healthy for at least 10 seconds before you place another one. And I want you to give it at least 3 minutes to become healthy. If it doesn't become healthy after that, consider the allocation unhealthy. And if it's unhealthy, you can optionally auto-revert. So Nomad can revert you back to a healthy job version. So how do we do this? Well, the deployments are based on allocation health. So if you're not using console, what Nomad will do is it makes sure that the tasks you specified, all the artifacts download, the configs render, the actual process has come up and stayed up for the configured healthy time. And if you are integrated with console, we'll reach out and read all the checks you've registered to make sure that those are passing as well. So not only are you up, you're actually healthy. So we also support canary deployments as well. So not every application that you're as comfortable just rolling through deploying. You might want to produce a canary that gets a certain amount of traffic, and the operator can read its metrics and logs before they're comfortable with deploying. So you can annotate that update stanza with a canary count, and when Nomad detects that change, it won't touch any of your existing allocations, but it'll place canaries out there for the operator to then inspect, and when they're ready, promote, at which point Nomad will continue a rolling deploy. And you can see this in the UI as well. So in this case, we have initiated a rolling deploy for a task group that has 3 instances running. And in this case, Nomad has placed 2 of them, and only 1 has been healthy. So it's waiting for that second placed one to be healthy for that 10 seconds before it places a third one, removing one of the older instances. And it will continue that till they're all done. So Nomad also tracks job versions nowadays. So in this case, it knows that you've updated the payments version from 1 to 1.1. And if this was unhealthy, it knows the difference between that and the last healthy version. So it can automatically revert you back to the healthy one in the case that you've done a bad rolling deploy. So that's deployments. Next is Nomad Plan. Nomad Plan allows job operators to do a dry run of the scheduler. So if you have a change and you want to know what the scheduler would do if you ran it, you can do Nomad Run. So this helps you catch mistakes before they would actually impact production. So what it would look like is, in the case that I had an update stanza with a canary, if I did Nomad Run, Nomad would detect that the change of 1 to 1.1 of my Docker image is a destructive change, and it would produce one canary. So before you even run it, you can be confident in what you're doing, and Nomad will give you that instantaneous feedback to make sure you don't make a mistake. Cool. So we're now entering the much larger deployment scales. And at this point, job operators have all the features they really need, and it's more about the operators introducing policy enforcement to keep the cluster healthy and within what security profiles they want. So we introduced Nomad quotas, namespace quotas, and Sentinel policies to do this. So what namespace quotas allow you to do is you can create a quota specification that says this quota object allows maybe 50 gigabytes of RAM to be consumed and X amount of cores. And you can attach those to namespaces. And then what Nomad does is, as it's running jobs, it'll determine whether all the jobs in the namespace are under the specified quota. And as soon as they touch or exceed it, well, hopefully not exceed it, as soon as they touch it, Nomad won't allow any more placements in that namespace. So this is important because it allows you to prevent a single bad actor from consuming all the resources of your cluster. You could imagine maybe one job is programmatically creating other Nomad jobs, and they have a bug. And all of a sudden, instead of creating one job per second, they're creating a hot loop of jobs, consuming all the cluster's resources. So you really want to introduce quotas to ensure that one bad actor can't consume all the resources of your cluster. And this provides QoC for other namespaces, which should be isolated. It's not just about isolating jobs on a particular node. Cluster-wide is important as well. So next is Sentinel policies. So the problem that Sentinel is trying to solve is, how do you enforce certain criteria against all jobs in a cluster when they're really fine-grained? I have ACLs to prevent people from interacting or reading jobs that they shouldn't be. But how do I enforce very specific things like they're only pulling from a particular Docker registry, the one I set up and I know is secure? How do I prevent them from using latest image, because who knows what that's running and it doesn't follow immutable infrastructure practices? Or I don't want anyone deploying to a production namespace on Friday, because that's how you have outages. So those are the problems Sentinel tries to solve, and it does it as policy as code. So the operator defines Sentinel policies, checks them in, version controls them, and they provide these incredibly fine-grained ACLs. So here's an example Sentinel policy for Nomad. I could write this Sentinel policy that says, I want every driver that is used in this cluster to use Docker. I don't want anyone to use any other type of driver. No raw exec jobs are allowed. And then you can submit this by just doing Sentinel apply this policy. And then if someone tries to run a job that says, I'm actually using raw exec, the policy will deny access to submitting that job. And it says, sorry, you don't meet the policy that's being enforced on this cluster. So I hope you enjoyed. That's some of the features we provide with Nomad to make sure that you can scale without introducing complexity into your stack. This is truly a driving philosophy behind our development. We always want to provide you with powerful and easy-to-use features. So with all those features I showed you, I built the final server config, and it was roughly 30 lines of code for everything. So I don't know where we landed on this scale, but I know we didn't land here. So thank you very much.